Hello everyone, welcome to lecture 5 of module 5, which is on 3D NAND flash memories. The disclaimers remain the same. We were discussing about the BICS 3D NAND flash memory, and we kind of got to know that just because the source select transistor was kind of at the bottom, so it was less accessible and its transistor properties were very difficult to control. And there were two other issues because of exposure of the tunneling oxide to the etchant while fabrication of BICS. The quality of tunneling oxide or the reliability is low. And the third issue was related to the source line, since it was N plus diffused source line. So the kind of resistance that it offered was high. So what people told was, or what like Toshiba came up with, was this 5 BICS. So what they kind of did was, instead of having a kind of vertical channel, they kind of turned it like this and then took it back towards the top. So they kind of made a pipe-shaped channel. And what they also did was, they kind of started taking the source line contacts on the top. So let me just highlight that. So the source line contact was also taken at the top, along with even the bit line contact. So this was the innovation. And since you have now your source line control or your source line contact at top, so you have better control over your source layer select transistor. And instead of using a N plus diffusion, they also replaced the N plus diffused source line with a metal layer. So on top, you can actually use metal layers. They kind of replaced this N plus diffused common source line with a metal layer, and then it leads to a reduced series resistance. And allows you through this fabrication process of 5 bits. So the first process in the fabrication involves formation of this gate conductor. So let me write it. The first 4 processes patterning this gate conductor. So why is it called the gate conductor? Because this thing which you see, which is kind of in black, this is kind of a gate, or this is kind of a polysilicon. This is not exactly your insulator. And within that gate conductor, then the deposit of sacrificial film. What is sacrificial film? So during later stages of the fabrication, it will be etched. So that is why it is called sacrificial. So the first process involves defining this gate conductor and then depositing of this sacrificial film. And then second step, what you do is you kind of deposit stack of polysilicon and insulator like you did in BICS. And then you etch the holes like this. You etch the holes or you kind of punch it like we did in BICS. Then in the third process, what you do is you use the etchants and you etch the sacrificial film. The sacrificial film which you kind of deposited in the first process, right? So this is what you do in the third process. And now you have this kind of a pipe kind of structure. Now what you do? Now you first, in the fourth step, what you do is, now you have that pipe structure. So first, you deposit your ONO. So first, the blocking oxide is deposited. Second, the nitride film is deposited, or the storage layer is deposited. And at last, you deposit the tunneling oxide. And then, in the last step, you deposit your polysilicon. And this kind of pipe structure allows you to, not use that etch, like here, since it's a pipe structure, and you don't have to connect to the bottom N plus diffusion layer. So here you don't have to expose the tunneling oxide to any kind of etchant. So this way, here what happens is the quality of tunneling oxide is improved. So the advantages you get: first, because of this pipe-shaped channel and taking contacts at the top, you kind of achieve a reduced series resistance. So here you achieve a reduced resistance of the source line just because you are replacing it with a metal and you are taking it at the top. Quality of the tunneling oxide is improved, and also the SLS transistor is at the top, which means that you can easily control its properties. So all the three issues that were there with the conventional BICS were kind of fixed with the help of this pipe-shaped BICS. However, here there is a fact that once you are using this control gate here, once you are using this gate conductor, so if you look at its kind of equivalent representation, so you have something like this. So you have this series of cells. Then here you have another cell, and then you have again these cells. So let me just draw it again. So this is your bit line selector. This is, let's say, your bit line. This is, let's say, your source line, which is here. And then you have these cells. These are different control gates. Here also you have different. Here also you have different control gates. Then here you will have your source line select. However, here also you have something which is called pipe gate. And this pipe gate is introduced just because you have a gate conductor over here at the bottom. So in your assignment, I'll also give you to find out the application of this pipe gate. Find out why they use this pipe gate. A hint is that you can kind of isolate the operation on the left hand side of the pipe gate and on the right hand side of the pipe. Okay. So with this kind of discussion on the fabrication of the P-BICS and the advantages of P-BICS, let me go ahead and see how we kind of pattern the P-BICS, how we kind of take contacts to the P-BICS. So here also you follow the same staircase pattern, but here if you look, so you have this source line which kind of connects. So this is one string. So you have one string like this, and you have another string like this. So you have one source line which is kind of common to two strings, and in between, instead of a plate, you have two different branches of these control gates. So here you see the control gate is not like a plate which is going through all the pillars, but it is only going through two pillars at a time. So here you can see these holes kind of correspond to each pillar. So you have one control gate which is kind of going only to two pillars. So let me write that. So one control gate only intersects with two adjacent pillars. So CG is not arranged in the form of a plate, which was in BICS, but it's arranged in a fork shape. Arranged in fork shape. Right? So you have this kind of a fork-like structure, which is shown over here, in which these CGs are arranged. And how you kind of combine these CGs. So you take connections to these forks. So connections to the CG forks are taken in staircase manner itself. So here also you have that staircase connection, and then you just kind of take vias and connect one metal line to that, and you kind of access those different control gate forks instead of control gate plates, which was there in your BICS. Also, what these people came up with was this. So you have these source lines which are on the top, and you have to kind of come up with a common source line for all, right? So what they did was, instead of connecting them with a metal layer, they used a top source line plate and then connected all individual source lines to this plate, right? And just by doing that, since it's at the top level, so as you go towards the upward metal layers, their line resistance reduces. So this way they were able to reduce the common source line resistance even further. Do you remember something like that which we discussed, while discussing about SRAM cells? Do you remember bootstrapping? That we kind of, to reduce the series resistance, what we do was we take this to a higher level of metal, which shows you a lower series resistance. So this is an example of bootstrapping itself. So whatever they have done is also an example of bootstrapping. They kind of took these individual source lines, which were present at some lower metal layer, and they kind of took a top level source line plate and they connected to it so as to reduce its resistance further. And once its resistance is reduced further, some noise immunity is also improved. So this was all about your pipe-BICS, pipe-shaped BICS from Toshiba. Now let us go ahead with what Samsung came up with. So Samsung came up with this TCAT, terabit cell array level transistor. After several unsuccessful ventures like VNAND. I guess I already discussed about the VNAND, which was its attempt in 2008, then ZVRAT and then VSAT as well. So after these unsuccessful attempts, Samsung came up with this TCAT, and this TCAT. So let me write this. So this TCAT formed the basis for all future generations of 3D NAND flash from Samsung, like VNAND, ZNAND, and even the most recent ones. So this was kind of developed in 2009. So this was developed in 2009. And if you look at the bird's eye view of this TCAT structure, you won't find much difference as compared to your BICS or P-BICS. So with respect to P-BICS, yes, there is a difference. Here the channels are vertical itself. It's not arranged in pipe shape. Also, as compared to BICS, where there was a common source line which was N plus diffused, here also the source lines are N plus diffused, but there are several of them. So it's not like a one big plate. So there are several source lines. So if there are several source lines instead of one plate, so you can already understand that the resistance is kind of low as compared to that. So how it is fabricated? So let us look at that. So also here, unlike your BICS, where it was a gate first process, in TCAT, what we use is metal gate replacement process. It's not replacement, but it's kind of metal gate last process. So gate electrode is defined at the last. So how exactly that is done? So initially, we first kind of go ahead and make these memory plugs. So here memory plug formation is also different. So here what we have is, you have these, here the stack that we use. So let me just go ahead and first go through the fabrication and then come back to this point. So how this TCAT is fabricated is, so in the first process, you have this, first what you do is, you stack layers of insulators. And these insulators stack can be, these insulators can be SiO2 and Si3N4. In BICS, what you used to do? So in BICS, it was insulator plus polysilicon, right? But here, it's not polysilicon because we told that it's not a gate first process, it's a gate last process. So here you first deposit the insulators. Like this is your oxide, this is your nitride, this is your oxide, this is your nitride, then again oxide, then nitride. So deposit stacks like that. And then what you do is, in the second process, what you do is, you etch holes and then deposit polysilicon. So once you do that, you arrive at something which is like this. Okay, now let me discuss about gate formation. So this is your third process, which is shown here. So in third process, what you do, you kind of etch between the pillars, between your polysilicon pillars. And this process is known as W/L cut. It's called word line cut. And it's used to, kind of define your metal control gates. Then what you do is, what is your critical kind of process here? Then you move on to this. So here you etch your nitride layer. So wherever your nitride layer was there, you have to replace it with metal control gate. Okay, so first you etch the nitride layer. This is your fourth process. Then in the fifth process, what you do is you deposit your metal control gate. And what are the metals that they use? They usually use tungsten. So before deposition of this metal control gate, what they'll do is, even before deposition of metal control gate, they'll deposit the ONO layer, right? Because this ONO layer is kind of very essential. That is where the entire operation is taking place. So immediately after this etching of nitride, they kind of deposit ONO. From here, they kind of then deposit ONO. And then after this, they come here, they deposit metal. They deposit metal like tungsten. So tungsten, why tungsten? Because tungsten and titanium nitride, these metals can flow. These metals can be deposited at low temperature. So let me write that. So tungsten can be deposited at low temperature, and it's CMOS compatible as well. You may have read that it provides you good adhesion property with your underlying substrate. So this is used for your source drain contact plugs, and then on top of this you use a titanium nitride. So that is why you use tungsten. It can flow easily at low temperatures, and it is CMOS compatible. So you kind of deposit these metals, and then what you do is you separate, like in the sixth process, you separate these control gate nodes by etching, right? So here you kind of separate two control gate nodes, and because of this separation, you do not end up having a control gate plate like PICS, but you have separate kind of control gate electrodes. Okay, so now that we have discussed about the fabrication, let us go ahead and look at what exactly this WL cut, what is the importance of this WL cut. So once you have defined this WL cut, I mean, this is your WL cut. Like, let me use red pen. So this is your W/L cut in between your gate electrodes, like control gate electrodes. So what they do is, how they realize this source line diffusion is, they kind of ion implant underlying substrate. The ion implant the underlying substrate and dope it at N+. The ion implant through this word line cut. So they kind of ion implant through this, and they kind of dope this region N+. Kind of dope this region N+. And this N+ region is nothing but your source line. Not common source line, but it's your diffused source line. N+ diffused source line. So this is how they kind of generate this N+ diffusion source line. And since this source line is not a very large metal plate, so its series resistance is low as compared to your PICS. However, if you look at this diagram, you will see that since there is no N+ substrate, I mean where you have your common source line like PICS, since this is not there, you have your P plus substrate also, which you can contact. So because of this, here you don't need, since you have this P well. So let me just write it here. So you have P well here. In TCAT, you have P well. In TCAT, you have P well. You have access to P well. Just because you have access to P well, what this gives you, or what advantage this gives you. So this gives you an advantage that you can perform erase similar to what was done in CTE memories. So GIDL is not required for erase. That is the advantage that this TCAT structure gives. There are other advantages as well, which we'll discuss. So yeah, so first let me write that here as well. So this TCAT Samsung came up with in 2009. So 2009 TCAT, sorry, advantage. So we had this option of bulk erase. No GIDL was first. So then they kind of improved upon this and they introduced this concept of staggered pillars or holes. So this is your bit line. This is your bit line. This is your second bit line. And in between those bit lines, this is your bit line. This is your second bit line, which is adjacent to it. And in between, they kind of arranged their holes or cells like this in a staggered fashion, so as to extract, or so as to use all the area which is available, or so as to increase the area efficiency. So your staggered pillar structure was introduced in VNAND as a kind of evolution of TCAT, and that led to what? Efficient utilization of area. Then what they did was they even staggered the bit line contacts. So instead of one bit line, they now had two bit lines. So they had these staggered cells like this. They had staggered pillars like this. And then instead of one bit line, they started using two bit lines. So what this helped with? This helped in increasing bit line density by 2. Then so this was introduced in VNAND generation 2. Then they again came up with a very efficient program pulse control scheme, and that program pulse control scheme used, so this scheme, let me write, so in generation 3, they came up with a very good programming algorithm, programming or erase algorithm. So what they did was they had different program erase voltage for different control gate layers. So this way they were able to optimize, their operating conditions and all. So this is how your Samsung's VNAND has evolved. So till now we have discussed about this vertical channel 3D NAND cell. There's another possibility which we discussed earlier, which was vertical gate and horizontal channel based 3D NAND flash cells. So let us discuss somewhat about that as well. So Samsung was kind of the pioneer, I would say, this kind of vertical gate / horizontal channel, which is also known as VG 3D NAND, was first introduced by Samsung in 2009. So parallelly, you see, it was also working on this vertical gate as well as on vertical channel. So this is how these industries are, innovating. Means that you have a channel like this, which is going in the horizontal direction, and you have gates which are going like this. This is the top gate, this is the bottom gate, something like this. So it's like your channel is being covered from two sides using these gates. So it's kind of twin gate or a double gate technology. So this is about the vertical gate. So let us first discuss about the first kind of vertical gate kind of 3D NAND flash, which was introduced by Samsung. So let us look at its process flow first. First of all, let us look at how you can fabricate this kind of a vertical gate NAND flash, 3D NAND flash. So first, what you do is you have this substrate, and then on top of that, you deposit this common source line. Deposit this common source line, and you kind of take its protrusion even towards top. So let's say that is the first step. So in first step, first define your common source line, and then you also define your source line selector. So you define your source line selector. Then you define your different word lines or your different control gates like this. So you define control gates or word lines, whatever you call it. Then the bit select line electrode, and then your bit line electrode as well. So you define these here. And then what you do, in the second step, you deposit polysilicon, which will act like your channel and insulators, which will kind of give you insulation between two subsequent channel layers. So that is what you do here. You kind of deposit different active layers of insulator and channel, polysilicon channel. Then in the third step, what you do is you kind of deposit your ONO layer. You deposit the ONO layer on top of this polysilicon channel or on the sides of this polysilicon channel. So if you have deposited these stacks like this, so if you deposit something on top, it will, like, the ONO layer will be on this side and it will be on the opposite side as well. So it will be covering your channel from two sides, and that is why I told that it's like twin gate kind of architecture. Anyways, so once you do that, then what you do is you go ahead and form your vertical control gates or word lines. So then you kind of form your vertical control gates like this. However, there is a stringent condition that these vertical gates, the vertical gates have to be aligned with your definition of this word line, bit line, and CSL that you did in the first step. With the first step definition. So that is there. You have to align these vertical gates with the BL, WL, and CSL that you defined in the first step. So this alignment kind of restricts the lateral scaling. So this kind of alignment restricts the scaling of these kind of structures, like the spacing between the gates and all. And at last, what you do, like in the fifth process, what you do is you just form contact plugs. Contact plugs to your bit line, your source line. Yes. So this is how you kind of fabricate it, and this is the final structure. So here the problem that they faced was that you had to kind of come up with an alignment between vertical gate and the horizontally deposited word line in the first step. So this kind of limits their scaling capability. So what what MACRONIX came up with is another structure. So MACRONIX is another company which is very innovative, and this is their vertical flash, and it is their vertical gate NAND flash. So MACRONIX in 2011, they came up with this structure where they kind of eliminated the formation of this bottommost source line. So what they did was the first what their innovation did is first they kind of eliminated the need for that embedded, I would say that embedded source line or bit line. So they kind of eliminated that need for that. So how they kind of came up with this structure? So first, they also kind of deposited the polysilicon channels and the insulators. So let me just use two different pens. So the first deposit polysilicon channel, then they deposit an insulator, which is not shown here, but they deposit an insulator. There's an insulator between the polysilicon channels, and then they again deposit the polysilicon channel here. And then what they do is they pattern it, or then what they do is they kind of, so let me just try it. So first, what they do, they kind of deposit what? Deposit insulator and undoped polysilicon stack. And after this, what they do? Then they pattern it. So in the second step, they pattern it. So by patterning, what I mean is they kind of divide it into several sticks. So let me use a different pen. Actually, it's very difficult to explain this using a 2D kind of approach. So I'll request you guys to kind of go through the book chapters really well, because it would be difficult to understand it for the first time. Just by looking at the 3D kind of structure, you won't be able to understand. So what I mean by patterning is, what they do is they kind of see, you can see here that your N plus is only limited, like this channel is only limited to this. So its thickness is kind of limited only to this. So they kind of pattern it to what, for what purpose they are patterning it? To define the channel thickness. So the pattern is to define the channel thickness in the Y direction, I would say. And then what they do is they deposit ONO layer. So in the first case, what they did was they kind of deposited an entire plate of this. They first deposited an entire plate of this kind of polysilicon. Then in the second step, what they did, they kind of isolated it into several different small channel plates like this. So let me just remove this. So in the second step, they kind of defined something like this. It's very difficult to draw. I guess you guys should understand. Yeah. So they defined something like this. They kind of segregated different channels along this direction, and then they deposited ONO. So then they deposited ONO to cover everything. So then they deposit ONO layer like this to cover everything. And then the fourth step, what they do is they deposit the gates, the gate material. And what this gate material will do? It will fill all this space which is left. So the gate material will fill this space. It will fill this space. It will be on top of this as well. So the gate kind of fills this space. It is on top of this. It is on top of this as well. So after this, what they do is, once the gate fills all this space, they kind of perform the gate patterning, right? So they kind of pattern the gate. So this is how they arrive at this kind of a structure. It's a very complex structure, but the fabrication is not that difficult. And then once they have this kind of structure, then what they do is they have to take source line and bit line contacts, right? So for source line and bit line contact, you see that they etch these kind of contact plugs. So they kind of use contact plugs, define these contact plugs, which kind of are attached to different channel layers. You see, this contact plug is kind of attached to this channel layer, to this channel layer, to this channel layer, to this channel layer. However, the kind of problem that they face here is you have these different strings, right? So you have one string, you have this second string, you have this third string, you have this fourth string, and the strings are horizontal. So let me just try. So here the strings are horizontal, So you have horizontal strings, but the problem that they face is how to select one string uniquely. And why this problem arises? Because even your source select transistor gate, I mean, let me draw it with a different pen. It's really difficult to explain this. So here your source select transistors are kind of common. They are going to all these pillars at the same time, right? Even your gate source select transistor is common to all the pillars. So it's not like PICS where you can, where you have orthogonal connection between bit line and bit select line, and bit select lines are kind of independent. Here you have this bit select line or bit select transistor is independent. Here you have these, GSLs and SSLs, which are going to all of these pillars. All of these, not pillars, all of these kind of horizontal strings. So how can you uniquely select this one or this one or this one or this one, utilizing just GSL and SSL transistors? That is very difficult. So what they came up with for this is, they came up with an idea which is kind of using redundancy, I would say. So what they do is, instead of having one SSL, one source line selector, what they do is they have different SSLs like this. So instead of having only one select transistor, they have like several of these SSLs, and in different layers, I would say in different layers of strings, like these are different layers of string, right? So in different layer of string, these transistors are kind of made up of different, I would say these are different kinds of transistors. So SSL is not same for different layers. So what do I mean by that? So one issue with having multiple SSL is that you add to your area overhead. I mean, your array area increases. And second, what they do is they kind of, design SSLs at different layers using different kind of transistors. How so? So what they do is they kind of integrate both depletion type transistors . So what are those depletion type of transistors? So usually they are on. They are normally on, and they turn off only when you apply some voltage. And enhancement mode transistors. So what about enhancement mode transistors? They are normally off and turn on only when you apply some bias. So just by using different kind of transistors. So here, if you look at this figure, you will understand that for each layer they make different SSLs using different technology. Some of the SSLs are depletion type, some of them are enhancement type. So the ones which are shaded with gray, they are kind of enhancement type, and the ones which are not shaded, like these ones, they are your depletion type. So they are usually on. So to kind of select one particular string, they use some combination of voltages at these SSLs, so that they uniquely select only one layer at a time. So this kind of a big, I would say, this is leveraging technology, and it's like they cannot make it in a single go, because the process for depletion type and enhancement type is not same. Actually, the channel doping is different in the two cases. So just because of this, they cannot, fabricate this at once using a self-aligned process. So achieving two different types of transistors on the same layer is kind of very difficult, and this is kind of what makes the process very complex. So it's a complex process, and it also increases the area overhead. And on top of that, one more thing that I want to clarify here is, for this VNAND, since the cross-sectional area or the cross-sectional shape is rectangular, it's rectangular, and you don't have gate-all-around structure, it's a double gate structure. So because of this, erase saturation can happen. And just to remove that erase saturation, what people do is, instead of using a usual kind of Sonos memory, they used a band gap or band engineered Sonos. So they use PE Sonos stack for this VNAND, just because the cross-sectional shape is different and it's not a gate-all-around structure. So it's process-wise very complex, because you have to add these SSLs, and in each layer you have to make some as depletion, some as enhancement type, and on top of that you have to even pattern these gates a lot more times. So these things makes its process complex as compared to a vertical channel kind of configuration.